Hi, welcome to this lecture on environmental adaptation of animals. Now we will expand the circulation out from the heart. So let's look first on the blood pressure. We quite often think that if we have the higher pressure, the blood will flow on the lower pressure areas. But actually, it depends on the energy of the blood. So we can have different kind of energy forms in the blood. And of course, the major consequences of the blood flow is caused by this potential energy of the pressure produced by the heart. So when we have ventricle cells, they are contracting, then they are pressing the walls of this ventricle chamber smaller and smaller. But if we have these valves closed, then the pressure is just increasing and increasing. And then the thing is that, if we have the valve open, then we have the blood flowing. And that's kinetic energy. It's much smaller than this potential energy, but it's enough to empty the ventricle to aorta on a short term when the aorta is already having higher blood pressure than the ventricle. And then the third term that it depends on is on the Earth's gravitational field. So when we are pushing the blood to brains or legs. On the brains, we must do more work to put it away from the Earth. And on the legs, we then must do work to push the blood back to the heart. And it depends on the height, and we can test it actually with a glass of water. So the glass of water, there's a liquid pressure, but in the bottom of this glass there is actually a little bit higher pressure because all the liquid above it is trying to go to the center of this planet. And so that's why the pressure is a little bit higher. And this is something that we are used to face in deep oceans, etc. But it also happens in the human body. So if we are raising hand, the blood pressure is much higher than in the legs. And we can calculate it quite easily. So it's actually 1 millimeter of mercury per 1.3 centimeters. And so above the heart, the pressure is lower, and below the heart, it's higher. And so one example where we are facing it is on the orthostatic movements. This is something that we do on the laboratory exercises in the bachelor courses. So when we are laying down and then standing up, the blood pressure is temporarily changed. And if the blood pressure is anyway very low, then it might be that, we are fainting. But usually that doesn't happen in our laboratory, but it will be some drop in the blood pressure. But then our circulation is compensating this on these orthostatic movements, etc. And what about then on the tall animals? This is very nice. Tobias Wang in Denmark, they've been studying a lot of these giraffes. Of course, Denmark is not the very natural habitat of this giraffe, but we have these zoos. And the head is about 3 meters higher than the heart. And you can see that the blood pressure in the head is very much lower than the blood pressure in the heart. And in the heart, the mean blood pressure is very high. So the systolic pressure is 200, diastolic very high also. And this is required to support the blood for the brains of the standing giraffe. How they've been doing it is they are using the male giraffe only, and on the anesthesis, they are then raising the head with a lifter or lowering the lift. And then they can measure what is the blood pressure in these conditions. And you can see that when it's drinking, the blood pressure in the head, as well as all the time in the legs, is about 300 millimeters of mercury. And even the diastolic pressure, so this lower pressure, is very high. And that means that, okay, there is a very high blood pressure also in the veins of these animals. And it seems to be that this animal is having very much different kind of compensation mechanisms. It has quite large heart to produce to get enough blood in all places and to maintain the high blood pressure, etc. Okay, what about then the flow and the size of the vessel? And on that we can go on the Hagen-Poiseuille equation. So let's assume that the animal is on the horizontal position, and in that case it's mainly produced by the heart. So it's just that, okay, the heart is contracting, and that causes the pressure first in the aorta and then in smaller and smaller and smaller arteries. And then we can calculate easily that, okay, what is the pressure difference? So how much pressure is on the other ends of this artery? And then there's a small equation with the viscosity, and over there we have the radius. So the diameter of this blood vessel. And you can see that there's this number 4, indicating that this is times 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 And that then means that, okay, if we have larger blood vessel, the flow rate is very high. But if we are having smaller blood vessel, then the flow rate is very minimal. And it's related on the viscosity. So over here we have these walls of the blood vessel, and beside them the blood is not flowing at all. So it's mainly flowing there in the center. And that means that, okay, if you have a smaller and smaller blood vessel, then more and more blood is on the contact of the walls. And that will cause that, okay, now the viscosity is reducing the flow. And quite often we also only need the difference. Okay, what is the partial of the pressure difference, and then we use the vascular resistance for all these parts. But it's good to remember that in different size vessels, the flow rate is anyway different. Okay, how this blood pressure is affected by the structure of these blood vessels. So first of all, we have the contraction of the ventricle, and in the previous video we were demonstrating that the pressure difference in the ventricle is enormous. So it rises from maybe 20 millimeters of mercury to 120 or whatever. And in the arteries, it's the difference is much smaller. So the diastolic pressure might be something like 80. So it's never going so low. And the other thing is that it's delayed. And that's caused that, okay, when we are pressing with the ventricle, it will bend the sides of the arteries. We have a very much elastic fibers, etc. there, so it acts as a rubber band. And that's caused the pressure damping effect. So when we are contracting the ventricle, the pressure in these arteries might be a little bit lower, and it definitely going to be a little bit slower because it will bend first. But then, after the reaching the higher pressure, there is this pressure reserve effect. So now this banded blood vessel will of course go back, and that will cause then this delay that, okay, it will short by little by little the pressure will go down, and actually it will be all the time much higher than in the ventricle. Okay, let's have a short look on the structure of a blood vessel. This is a very typical, so you can see that there are several different kind of structures. This structure is completely different than this one, etc. And we have 3 layers in typical blood vessel. So the outer layer, that is connective tissue, blood vessels in the circulation, so there might be some small blood vessels to give oxygen and nutrients for these all these tissues. Then there's the middle layer, which has the smooth muscle cells, and then a thinner layer that has the endothelium. And these our layers might be thicker or thinner in different kind of vessels. So when going from the heart to the capillaries, so we first face elastic arteries about 1 centimeter wide, then maybe 2 millimeter wide, then these millimeter size terminal arteries, and then the something that is very difficult to see. So if it's smaller than 0.1 millimeter, then we have these arterioles. And what we can see that, okay, in all these there is smooth muscle. And in these large ones we have these elastic lamelles and connective tissues and etc. And then in the smaller we have more these collagen fibers, etc. And you can see that the smooth muscle, there is less and less layers, so less and less cells on the top of each other. And so that means that, okay, that the wall of these blood vessels is over here. It's very thick, and over here it's thin. But at the same time, the diameter of the blood vessel is also smaller and smaller. So actually, in the small, thinner, so it might be that if we have the blood there in the center, there might be as thick layer of this wall around it, whereas over here we have large cavity there in the center, and then this layer is much smaller to compare the size there inside. And when we are having the blood, testing the blood pressure in different parts of our body, we can see that in these large arteries and terminal arteries, the blood pressure is quite high all the time, and it doesn't drop so drastically. And although still these small arteries, they have thinner walls, so there is less cell layers, but because the flow rate is smaller, so we have also the Laplace law that we are not going to discuss more, that it affects so much on the tension. So we can have smaller diameter, then there might definitely they are not going to bend these walls so much as in these large arteries. And then it's dropped drastically in the arterioles and definitely on the capillaries. And you can see that the blood pressure is actually very minimal in all these veins. So when it's coming back to heart. And why we have now over here this drop of this pressure is because the total surface area. So the total surface area is not rising much before the arterioles, and it's maximal here in the capillaries. And that means that, okay, you are pushing the blood in larger total volume, and therefore the pressure will drop so drastically. And also, when it goes on these small vessels and smaller vessels and these very minimal capillaries, then the blood, the flow is also very minimal. So it has two ways, because first of all the pressure is lower because the total surface is increased, but then also these vessels are smaller, so it's very definitely going to be a very minimal flow of the blood in these capillaries. And we can also regulate these arterioles. So when we have this is typical blood vessel, so there is endothelial, and below the endothelium there is these smooth muscles. And they are interacting. So if we have, for example, stress stretch and that increase, for example, activated platelets, so we have certain compounds that are released from the endothelium, and they are regulating the smooth muscles. Normally, they are they are releasing these vasodilating factors, and when we have any problems, then they are not anymore releasing these, but they are all releasing constricting factors. And because they are linked on these directly beside these vascular smooth muscle cells, they can regulate it. And this regulation can be very fast because there are these cap junctions. And beside that, we also have some ion channel regulation, so this electrical connection. We can also have differences in how to regulate it. And that means that, okay, we can then get these smooth muscles smaller, so they are contracting. And we remembered from the previous videos that, okay, they were contracting a little bit different mechanisms than these striated muscles. But anyway, when they are contracting, that means that will pinch the blood vessel. So the blood vessel will be closed because you have a ring of these smooth muscle cells, and they are contracting. So therefore, there is no blood flow. And one place where it's very important is on these arterioles, where they have a very thick wall to compare the size of the lumen. And that means that, okay, you can open or close this the circulation. So over here, there is no blood flow at all. So all the blood is flowing over here. And that causes that, okay, we have microcirculation beds. That, okay, we have these capillaries that are not going directly from the arteriole to venule, but they are forming this kind of map to give the oxygen and the nutrients to every cell between the arteriole and the venule. And the blood flow in each organ and even in this inside the organ can be then therefore controlled. So not all the capillaries are full of blood at the same time. We will open and close these valves. And one example where we can see this well is on the surface recirculation in the cold weather. So when we are in the cold weather, first of all, we can see that our body skin is turning red because we open more the surface circulation. And then later it might be becoming pale because we then close this circulation. Okay, so the circulation can also be modulated. Okay, we have different ways, different strategies. Some are very fast and some are very slow processes. So first of all, we can modulate the heart. If we have higher beat rate, so there is more beats per minute, and of course that causes that, okay, the flow rate will be increased. Or we can also regulate the contractility of a single beat. So when we have the ventricle contracting more, then there is more blood flow per each beat. And together they are affecting on the flow rate, so how many milliliters per kilogram per minute is the flow, and that affects on the systolic pressure. So during the ventricle contraction. Then we can affect on the smooth muscle cells. So the tension of the smooth muscle is affecting that, okay, how much this circulation is resisting, and that causes the diastolic pressure. And that affects also on during the ventricle refill. And then the third version, that is quite often something that we forgot, that, okay, we also can have differences in different animals on the blood volume. So if you have more blood, then your blood pressure is definitely going to be higher. Or you can also increase the carrying of oxygen with oxygen-binding molecules, so-called respiratory pigments that we are going to discuss next week. So we can have differences, and that's why even in humans we are when we are measuring the blood pressure, we are measuring both systolic and diastolic to reveal that, okay, is it because there is more tension because when we are getting old, for example, then our blood vessels are not so flexible, and that will increase the diastolic regulation. And or when we are having, if we have some heart problems, that could cause the systolic regulation to increase. Okay, and over here we have the blood pressure and the cardiac output of several mammals. We humans are quite average on this. So the systolic pressure depends on the heart, is about 120 millimeter of mercury, and the diastolic is maybe 80. So depending on the tension inside these blood vessels. And the cardiac output is about maybe 90 or 80 milliliters per kilogram per minute. And we can see that we have athletic animals like dolphins or horses. They have higher blood pressure. Both these indicators are higher. And in some cases, like this ground squirrel, the cardiac output can be enormous. In these small animals, quite often the cardiac output is very high because they have very rapid hearts. They are contracting the heart hundreds of times per minute. And then if we are comparing with the birds, these birds are also having quite high systolic and diastolic pressure. But then on the ectotherms, the systolic and diastolic pressure are typically very low, as well as the cardiac output. And why we have this large difference is because when we are pushing from the heart on the arteries, then we have these capillaries. Before turning it back to the heart with the veins. And we, mammals and birds, we have plenty of these capillaries to compare these ectotherms. And in the capillaries, the blood flow rate will be dropped drastically. And the blood pressure will drop drastically. And we can compensate it by having the high blood pressure in these arteries. Thank you.